Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to be going over the types of radioactive decay. So, the first one I'm going to go over is called alpha decay. And alpha decay occurs when you have an unstable nucleus and it emits a particle composed of two protons and two neutrons. So, in that particle, since we have two protons and two neutrons, that would be the same as a helium nuclide or a helium isotope because we know that for helium has two protons. That's what makes helium to be helium. And then in this case, it's got two protons. So for the mass number, it's got two protons and two neutrons. So that's going to be 4 for the mass number. And then the atomic number is 2. And so we write the symbol for helium. So this symbol would be the symbol for the alpha particle. We also use the alpha symbol, the Greek symbol alpha, to also represent the alpha particle as well. And so the way we write our equation, our nuclear equation, is going to be the parent nuclide, which is what the isotope that we begin with. This one has the unstable nucleus. That nucleus is going to emit a particle. So the particle is going to come from the nucleus. And then what's left is going to be a daughter nuclide. This daughter nuclide is going to then be smaller than this one since they lost the alpha particle. And so then we have the alpha particle here. So here's an example of a nuclear equation where the parent isotope is undergoing the alpha decay, and then the daughter isotope is left over. So here we have uranium 238. Uranium 238 emits an alpha particle from the nucleus. And so here's the alpha particle on the product side. So it's producing the alpha particle. And then what's left over is the daughter nuclide or daughter isotope. And so here you can see that the daughter isotope is thorium. And because the uranium lost a helium atom, the equivalent of a helium atom, that means it lost a mass number of 4. So you can see that 234 is 4 lower than 238. So it went down by 4. And then the same for the atomic number. It lost the helium nucleus, which has an atomic number of 2. So you're losing 2 protons. So 92 protons for the atomic number here goes down to 90 for thorium. So this is your daughter isotope. And then here's your alpha particle. And so one thing I'm going to point out, and this is the same for all nuclear equations, is that the numbers balance out. When you're balancing your nuclear equation, the atomic numbers on the top on both sides equal to each other as well as the mass numbers. So you can see the atomic number for uranium is 92. And so the total number on this side is 92 for your atomic numbers. That is equal to the total atomic numbers on the other side. And so that's going to be 90 plus 2 gives us 92. That's equal to 92 on this side. And that's the same for the mass numbers. And so here I have a total of 238 on this side. And then I have 234 plus I have 4 here. So that gives me 238. So the mass numbers, the sum of the mass numbers on this side of the equation is equal to the sum of the mass numbers here. Now, this is a basic equation, but you can get more complicated. Here, I only have one reactant, but I could have several different reactants on here. So maybe I have a neutron bombarding my uranium to make it unstable. And then maybe here I might have alpha decay. Maybe I have some neutrons emitted as well. So I could have several particles on this side, and then I could have several particles on this side. But the rule always holds. Balancing of the nuclear equation means that the sum of the mass numbers on top on both sides of the equation must be equal. and then the atomic numbers, all of the atomic numbers on both sides. The sum of the atomic numbers on one side must equal the sum of the atomic numbers on the other side. That holds true for all nuclear equations when you are trying to balance them. And so this also helps you figure out what your uh, daughter isotope is going to be. So you can predict what your daughter isotope is going to be if you know what kind of decay it's going to undergo. Okay, so what about alpha radiation? So alpha radiation is what is called, or may be called, the 18-wheeler truck of radioactivity. The alpha particle is huge. It's the most massive particle given off in any sort of decay, and so this is going to lead to it having the most ionizing power and the least penetrating power. So if you think of 18-wheeler truck during traffic, it's going to, if you think of an 18-wheeler truck trying to get through traffic, it's not going to go very far. So the um, the alpha particle, because it's so huge, has the least penetrating power. And if we understand penetrating power as the ability to penetrate matter, well, matter is made up of atoms. Those atoms and molecules are very close together. So an 18-wheeler truck, if we're using the analogy of getting through traffic, it's not going to get through traffic very well because it's so huge, right? So it's not going to be able to get very far past the atoms. Sorry about that. Light went off. So the alpha particle is not going to be able to get very far because as it's going through the matter, it's colliding with all of these atoms and molecules that make up the atom, and so it's going to be stopped pretty soon. So it doesn't have a high ability to penetrate matter. Which is a good thing, because if you have an alpha particle being emitted from a substance and it's outside your body, it'll hit your clothes, it'll hit your skin, and your skin and your clothes are going to be enough um, to block or prevent the further penetration of the alpha particle. So it's relatively safe to you. However, if for whatever reason you have alpha particle emitters in your food or your drink, and you ingest or breathe in the alpha emitter, then now it's inside your body. And so it can have access to your vital organs and living tissue. And so in that case, it can do a lot of irreparable damage and could be lethal. Um, so so it has the least penetrating power. So it's relatively safe on the outside of the body. It could be blocked by, say, a piece of paper could block it. Um, but it has the most ionizing power, and that's because it's got a large charge on it. It's got a charge of a +2, and so that's going to affect uh, other molecules and atoms as it's going through the material. So that high positive charge is going to be attracting electrons. It can pull electrons from bonds of molecules and break bonds and stuff like that, and cause other things to become ionized and become ions, and so that can wreak havoc especially if it's in living tissue that this is occurring in. So it has the most ionizing power, but it also has the least penetrating power. So that's alpha decay. So next is beta decay. Okay, so for beta decay, that occurs when an unstable nucleus emits an electron. So we saw in alpha decay. Alpha decay occurs when an unstable nucleus emits a helium nucleus with two protons and two neutrons. In beta decay, the unstable nucleus emits an electron. Well, how can an electron come from a nucleus is probably what you're wondering. Aren't the electrons outside the nucleus, moving around in orbitals? Well, they are, but it turns out that the nucleus is more complicated than it appears to be, or that we have, or that you may have heard. So, what's going on in the nucleus? Well, here in the nucleus, in order for an electron to be emitted, a neutron in the nucleus actually breaks apart into a proton and electron. And that makes kind of sense because we know that the neutron has zero charge, the proton has a positive charge, and the electron has a -1 charge. So we have -1, +1, you add 1 to -1, and you get 0, right? So here the neutron breaks apart and you get a proton. The proton stays in the nucleus. So now you've added one proton. So you lost a neutron that has a mass of 1 AMU, and you've gained a proton which also has a mass of 1 AMU. And so in this case, the mass number is not going to change, but you've gained a proton. You've lost a neutron, you've gained a proton, so now you have one more proton. And remember, protons determine the identity of the element. So if you change the number of protons, you change the element. And in this case, the daughter isotope is going to have one more proton than the daughter, than the parent isotope or nuclide. And so there you have the electron. So let me specify this a little bit more. So here we have our example of a nuclear reaction. Um, Let me start with this part here. So if we symbolize the neutron, the proton, and the electron using the symbols that I showed you in my last video, here we have the neutron. So we have the neutron with a mass number of 1 and a atomic number of 0. And that's going to break apart into proton, which is the symbol is a P with a mass number of 1 and an atomic number of 1. And then we have our beta particle, which is the electron, and it has a 0 mass number and a -1. And again, you can see that the mass numbers and the atomic numbers balance out. They balance each other. So if you look at the mass number on this side is 1. And then on this side, the total is 1 plus 0 is 1. So the total on this side balances with the total on this side. Same for the atomic number on the bottom. So the total atomic number on the bottom is 0 on this side. And the atomic numbers here, 1 and -1, add up to 0. So they balance. Okay, so here's another example of our radioactive decay. Here again, we have our parent nuclide, radium-228. Here we have the daughter, and here we have our particle. So the parent nuclide releases an electron from the nucleus. And so because it's releasing an electron has a 0 mass number, so the mass number is not going to change. So 228 stays 228. But remember, the neutron is going to become a proton, so now you're gaining another proton. So 88 becomes 89. That's going to change the symbol. It goes from radium to AC, actinium. And then there's the symbol for your beta particle. So here's your beta particle. So this is a good example of a beta decay. So how do we describe the beta radiation? Last time we said that alpha radiation was the 18-wheeler of radioactivity. Well, the beta radiation is going to be the SUV of radioactivity. So the SUV is much smaller than the 18-wheeler, and so we would expect that this particle is going to have a lower ionizing power compared to that of the alpha particle. Again, the The electron is much smaller. It has a much smaller charge on it. It's a much smaller particle. So the ionizing power is going to be lower compared to that of the alpha particle. And it's going to be, but it's going to have a higher penetrating power because it's much smaller. So, if, again, using the analogy of being stuck in traffic, an SUV is going to be able to get around and get through traffic a lot more easily than, say, a large 18-wheeler truck. So, um, so we can say that that's going to have a higher penetrating power. It's going to be able to penetrate further into the matter because it's a smaller particle and it can go through. So the best way to block an alpha particle is using either an aluminum sheet of paper. I'm sorry, an aluminum sheet or a block of wood. That's going to usually going to block. So paper or your skin is not going to be enough. So in this case, you need something that's a bit thicker and sturdier. And so that is our beta decay. So next would be gamma radiation. Okay, so next is the gamma ray emission. And gamma radiation is a form of electromagnetic radiation. So in this case, it's a bit different than when we're talking about regarding the alpha decay and the beta decay, because the alpha decay and the beta decay actually releases particles from the nucleus that have mass. In this case, you're releasing not a particle, but high energy photons that don't have any mass. So this is the symbol for our gamma radiation, our gamma particle, if we want to think of it as a particle. So our gamma particle is the Greek symbol gamma that looks kind of like a ribbon here. And we have a 0 for the mass number and a 0 for the atomic number. So this has no mass. So when you release a gamma ray or a gamma particle from the nucleus, the mass does not change. So this is usually emitted from a nuclei in excited states. So if you have a nucleus that's in excited state, or it also is emitted in conjunction with other types of radiation. So you can have an unstable nucleus that's excited. So in this case, here's an example where you have uranium again, uranium 238 is undergoing an alpha decay. So you have a uranium 238 with 92 atomic number. And then the daughter nuclide is thorium with 234 mass and 90 atomic number. And you have your alpha particle. But along with the alpha particle is some gamma ray. So you get a gamma ray emitted along with the alpha particle. This happens almost pretty much all the time. Anytime you have a different another radiation like alpha or beta, you're always going to have gamma radiation. So it's so frequent or so common that we usually leave this out of our equation. So we just keep it like that. But we know that there are gamma rays released as well. And the reason we get gamma rays occur is because imagine that you're losing a chunk of the nucleus. And so the unstable nucleus is losing a particle, either an alpha particle or a beta particle. And so when that happens, the particles, the nuclides or the nucleons in the nucleus have to kind of rearrange to kind of restable itself. And that rearrangement of the nucleons in the nucleus is what causes the release of energy, because it's becoming more stable, and that energy that's released is in the form is what we call the gamma radiation. Now you could have a release of you could have a nucleus undergo radioactive decay, and then the result could be what we refer to as a metastable daughter isotope, in which the alpha decay doesn't happen right away. So here, when you undergo this alpha decay, we can see that the radiation here for the gamma ray is released along with the release of the alpha particle. But you could have cases in which the time at which the alpha particle or the beta particle is released is not quite the same as when the gamma ray is released. So there might be a delay in the release of the gamma ray. And so what you have then is a metastable nucleus. So here, for example, we have this nucleus here, and you'll notice that we have the mass number on top with an M. The M means that this is metastable. So we have a metastable parent isotope. So this would be the daughter isotope after your parent isotope has undergone some sort of decay like alpha or beta decay. So here's the result. It's metastable, meaning that it hasn't released the gamma radiation, but it will at a later time. And so here you have the parent isotope then releasing the gamma ray, and then you have the same element, but now we don't have the M there because it's now stabilized after releasing the gamma ray. And so again, you'll notice that because you have zeros on the top and bottom, there's no mass for the gamma ray. The release of a gamma ray does not change the numbers of the mass or the atomic number. So these are not going to change for your daughter isotope. So gamma rays, to continue the analogy of vehicles, your gamma rays are the motorcycles of radiation. So they're going to have the lowest ionizing power, but they're also going to have the highest penetrating power. And again, if you can imagine a motorcycle, you've had experience of a motorcycle going through traffic, the cars and the trucks are stuck in traffic, or they're going very slowly, and all of a sudden you see the motorcycle zipping through past the cars. And so that would be the example of a all right, sorry about that. So, as I was saying, the analogy of the motorcycle being zipping through traffic, that's like your gamma ray because it's no mass. It doesn't have any mass, so it can get through matter pretty easily. And so, in order to block gamma radiation from harming you, this requires more extreme measures. So, as we said with the alpha particle is massive. So you can easily block that with like a sheet of paper. Your clothes, your skin can easily block it. So alpha emitters are safe outside the body, but if you ingest them, they are actually more harmful. Beta emitters, right? So beta particles, they're smaller, and so they penetrate farther. They have a lower ionization ability, but they have a higher penetration. So, in order to block beta particles, you need maybe thin sheets of metal like aluminum foil, or you need a few inches of wood. Would be like an example of something that can block beta particles. But for gamma particles, they have such a high penetrating power that in order to block them, you need a few inches of a thick metal like lead, or you need like a few feet of concrete. So those are the things you need in order to block the gamma radiation. So that's it for gamma radiation. Next, we're going to talk about positron emission. Okay, so the fourth thing we're going to talk about is the positron emission. So, positron emission is where an unstable nucleus emits a positron. So, what is a positron? Well, the positron, as the name kind of suggests, is an antiparticle of the electron. What that means that it is a particle that has the same mass as the electron, but the charge is the opposite. So it's the opposite of a negative electron. So it has a positive. So it's like a positive electron. That's the best way to think about it. So if a positron collides with an electron, right? What's going to happen is that they are going to annihilate each other, and they're going to release energy in the form of gamma rays. So that makes sense because you have a negative electron comes in contact with a positive electron. The positive and negative kind of cancel each other out. So you can imagine that they're going to annihilate each other and then release that energy in the form of gamma rays. And so, what's happening? How does the nucleus emit a positron? Well, in a very similar way as the nucleus emits an electron. We saw that when the nucleus emits an electron, that's where you have a neutron breaking apart into a proton and releasing an electron from the nucleus. So you have a neutron converting into a proton in the nucleus. And we saw that when beta decay occurs, the atomic number increases by 1 because you're adding a proton to the nucleus. Here, you got kind of the reverse going on. So you have a proton uh, converting into a neutron upon which a positron is emitted. That positive electron is emitted. So here is the formula. So we have our proton in the nucleus. That's going to break apart into a neutron and release the emitted positron here. And so here's the symbol of the positron. Instead of having a -1 on the bottom, we have a +1 on the bottom, and we still have the symbol E there. That lets us know that it's the same as an electron, but it has a positive charge. Um, so here you can see that when you do a positron emission, the bottom number, the atomic number, is going to decrease. So instead of increasing when you have beta emission, it's going to decrease when you undergo a positron emission. So here we have phosphorus 30. So we have a 30 on the top, and we have a 15 for the atomic number. And when it undergoes a positron emission, the 30 stays the same since the number of the mass is the same. 30 is going to be the same, plus you have 14 on the bottom, but we have 15 to start with. So you see that it decreases by 1. And like all nuclear equations, the top numbers and the bottom numbers balance out on both sides. So here we have a 30 on this side. 30 plus 0 is 30. And on this side, we have a 15. And here we have 14 plus 1 is 15. So the numbers on the top and bottom are going to balance out. As far as the penetrating power and ionizing power, they're very similar to the beta particle. So the ionizing power and penetrating power are similar to the electron. So that's positron emission. So next is going to be electron capture.